First, it's a pleasure to be here, and thank you for coming at this late hour. Thank you, Miranda, for the introduction, Jim, and also Richard Love, who's had a lot to do with this lecture. And then finally, I need to thank the Kavli Foundation, and especially Mi Young Chun, who's the Vice President for Science Programs, and Christopher Martin. They have a real vision for the Kavli Foundation, and you're going to see a lot of great things coming from them, because I had the pleasure of spending time with them today, where they mapped out their future vision for the foundation. And so today what I like to do is talk about this artificial leaf. I'm glad Miranda mentioned that my research advisor, Harry Gray, because it always starts with your teachers. And Harry, when I was a graduate student, instilled the whole energy bug in my blood, but really challenged us, and there was a whole cohort of students, all who have gone on, and stayed committed to the problem, because you got to remember in the 1970s, science energy went away. It was gone again. And I had no conferences to go to. Isn't that sad? So I couldn't go to any Gordon conferences. All my friends became organometallic catalyst chemists, and I just kind of hung in there on energy. And that's something Harry taught me, and so I like to thank him. So today what I'll do is talk about this issue, the artificial leaf. And before I do, since it's kind of a general lecture, you can see I give lots of public lectures because I have to spend a lot of time finding pictures on Google that are evocative of the image I'm trying to show. The Holocene is something that you're living in now. It started 10,000 years ago. But it was a time, and it's a period, an epoch, geological epoch, and it's where humans weren't really affecting the world because there weren't many of you. And we still live in the Holocene, but now there's this new word that's cropped up since the 70s, and it's called the Anthropocene. And the basic issue is there's so many of you, you've actually started affecting life systems. Right? So you're in an adverse way affecting the world because there's just a lot of you. And the reason I bring these two epochs up is because I think this community, chemistry, can start a new geological epoch. And it's actually something that's been discussed by an Australian physician, Brian Furness. And he calls it the Sustainocene. And the Sustainocene is what you would think sustainability, and you always think ecological sustainability or environmental integrity, climate change. But Furness said that's not enough. There is one other piece of this, and it's you. It's the people. And you can't have a sustainable world if you have a bunch of poor people in the world. And you can't have have-nots. And as the world develops, there's a bigger chasm between the haves and have-nots. And he's saying that's just not sustainable. And so one thing I'll pose to you today is this community can actually start a new epoch in humankind. Let the physicists do their thing. Who cares? The chemists can actually start a new geological epoch. And it's by giving food, water, and energy to the poor of the world. And by doing that, you empower them, and then they can start rising, and they can make money, they can become educated, and you start narrowing this divide. Now, why did this kind of hit home for me, Brian Furness's view of the world as Sustainocene? Because for energy, if you don't take care of these poor people, you're going to be in big trouble. So the energy equation has three terms in it: population, gross domestic product per capita, how rich a country is, and then energy intensity. Can you grow your GDP and use less energy? That's conservation. And it turns out you're all energy users, if you can calculate it, the number of calories you take in 24 hours and then calculate power, joules per second. And you're going to find out that you're all 100-watt light bulbs. And that's why you look so bright and shiny to me right now from up here. As more of you show up, of course, you're going to need more energy. And it turns out the numbers, and so remember, this is power, so I like talking about power energy per unit time. And you're burning a big light bulb in the world. You're burning around a 14 trillion watt light bulb right now, and you need to give energy to that light bulb to keep the light bulb on globally. And in the next 40 years, you're going to need around 16, 15 more terawatts worth energy equivalents. And so you're going to double your energy. In that calculation that I did, I assume, by the way, you're going to save all the energy you're using today. So you're going to need 16 terawatts, 15 terawatts equivalents of energy, and you're going to be saving 14 terawatts in the next 40 years. So I chose a very aggressive energy intensity number, this last number, EGDP. And so then the question becomes, and now you're going to see how this folds into Furness's idea of the sustainocene. If you need 15 more terawatts and you're saving all your energy, what's going on? Why? You're good citizens, science is going well, you're figuring out how to save energy, and it's because it has nothing to do with you, right? It has to do with the people we don't see in our lives, the poor. And so there's 3 billion people that are low energy users. Actually, people have been trying to give energy to the poor for 40 years, and there's more people than ever, 1.6 billion people without even electricity. So something must be wrong in terms of our approach. And then there's around 1.4 super low energy users, and there's 3 billion new people to come, and they're coming into that part of the world, so there's 6 billion new people who are going to need energy. And if they start reproducing what you've done and use coal, oil, and gas, the world's going to be in deep, deep problems. And if you think you've seen climate change so far, wait till you see what you'll be in for. So it's to your advantage to start taking care of these 6 billion people, and that's this issue of the sustainocene. You have to take care of those people if you want ecological sustainability. And then the question becomes, what have we really been doing wrong to get these people energy? Because, like I told you, the number's growing of people without energy in the world. And the problem is the way we do science. So we get funded from federal agencies, industry, and you take care of problems for this world. You guys are wealthy, and because you're wealthy, you can demand high-performing things. And it turns out, when we want to go to the poor, what we do is, I was at MIT, engineers abound. You take whatever you have and you re-engineer it, and you take the proverbial square peg and you pound like heck and you make it go into that round hole. And it turns out, if you start with these energy systems and start re-engineering them, first they're expensive to begin with, and then they just get more expensive. So that's why this hasn't been working. When we do science, I call it EST science, S science, the biggest, the fastest, the tiniest, the smallest. Once you start doing that, you're going to be talking about cost. So what you really need to do, and this is kind of a nice thing, you need to start inventing new science, work from the ground up. Like take a plain piece of paper and say, what science do I need to invent to start getting costs out? And a simple measure or a metric for cost is how much does it weigh. It's that simple. So I sometimes say, this is what Harry actually still does experiments. I've become totally useless. I sit in my office, I go on Google and I make Google plots, and then I run into the lab and I tell my students, look what I just discovered, and then I say, go back into the office, no sir, and leave us alone and let us keep doing science. So I'm going to show you one of my latest discoveries from Google. And what I did is I took just something like a Boeing 777, and I said, how much does it weigh? And then how much does it cost to manufacture? And how many did they make? And in 2006, there were 74 Boeing 777s made. Then I did it for etching tools, machine tools, and automobiles. And you get this curve. And without knowing anything about the sophistication of the technology, I can start predicting price. And what you find is things that weigh a lot cost a lot. And there's kind of a Darwinism of materials research, in case you've never thought about it. Almost everything comes out to $10 per pound. Now, it doesn't work for pills, pharma. It doesn't work for Intel chips. It doesn't work for commodity chemicals, but it works for machines, and this is how you build energy systems. And there's a magic number, $10 per pound, and that's basically stuff, right? It's stuff you dig out of the ground, it's wire, it's cement, and it comes out to $10 a pound. And it works for lots of things, like I said, and one of them, for instance, you can say Boeing 777s don't look much different than automobiles. This is true. I did call McDonald's, and I found out the weight of the patty, the cheese, the bun, and the lettuce, it's $10 per pound. All right, so McDonald's hamburgers, to me, don't look any different than Boeing 777s. Now, when you look at this graph, we're kind of simple thinkers. We say, how do you guys build energy systems? What you do is you build one thing, a power plant, for instance. It's centralized, it's heavy. You multiply $10 per pound, how heavy it is, and it comes out to around $1 billion. So if you want to build energy plants, you got to put out around $1 billion. And that means you need a high CapEx cost, capital expenditure costs, and then I set up some business model and I get a return on my investment. And thank God, that's how we build energy systems in the legacy world, meaning you're a legacy because you inherited an energy system, and now it sits like an albatross around your throat. The poor don't have anything because they don't have a lot of money to pay the big capital expenditure. So that's actually what is saving us right now. And so the real goal becomes not to build energy systems for them the way we built them for us. And if this part of the curve isn't working for them, this is science. If that end of the curve isn't working, turn your eyes to the other end of the curve. And the question is, can you start building energy systems like a hamburger? All right, so that's what I'll talk about. When I look at the artificial leaf, to me it's, could I build the hamburger of energy systems? Now, why do I care about weight? Because of cost. And that means I need to start thinking, if I'm going to do science discovery, and I want to innovate things, I should start thinking about what's the lightest lightweight materials and things I can make. And look at all these things here. These are all ways you can store energy, right? So I could have a solar panel on your roof, and I could pump air into the ground and compress it. And then it basically run the compressor backwards, that's a turbine, and you can generate electricity at night. So I could take compressed air energy storage and then run it at night. You'll get electricity. What you see here is that compressed air is 0.5 megajoules per kilogram. That's how much energy you can store. And by the way, I published this in Chem Reviews, and most of the articles on mechanical engineering, how flywheels work. And every reviewer pointed out to me that it was chemical reviews. And no, sir, it's not doing chemistry, so they rejected the paper. But you have to know who your competition is. So these are mechanical engineers. So they're tough. This is a tough crowd. And they're doing as well as people who do batteries. Look at batteries are 0.5 megajoules per kilogram. These are low energy storage devices. it's always been chemical bonds that you store most of your energy, because you get most of your energy density, bang for your buck, in a bond. It's kind of interesting. My entire talk today is freshman chemistry. So look how these look complicated. If I did energy storage for a battery and put an electron on a metal atom, because charge goes into the metal atom, so you take charge out, and I took the density of a solid, and then I put some number of electrons in there, then take the volume of a 2-electron bond versus the volume of putting electrons on an oxide lattice, you get that difference in energy density, 100 to 1,000 times more energy dense. And you know that because 100 years ago you decided to use fuels. You didn't use batteries. Now, you should use batteries if you're a car company, and if you can make your car go 4 times longer on a battery, you're going to become incredibly wealthy. Right? So you should do that. But you're not going to take care of storing 16 terawatts worth of energy for poor people in batteries because of that low energy density. So this is kind of a nice thing, because we're chemists and we deal with bonds, and that's where you're storing most of your energy. And if you don't like using technology as your benchmark, of course you can use biology, and that's photosynthesis. So photosynthesis stores energy, and from grade school you remember light, sunlight, plus water, plus CO2 gives you oxygen and sugar. What most people forget is all the energy storage and